And so in this example, we basically took an area, 90%, converted it to a z-score, 1.28, converted that to an SAT value, so 1.28 times our standard deviation of 100 gave us 128, and then we took those points and added it to the mean to get our score. Let's look at another one. So here we've got a tire manufacturer believes that the tread life of its snow tires can be described by a normal model with a mean of 32,000 miles and a standard deviation of 2,500 miles. If you buy a set of these tires, should you hope they'll last 40,000 miles or more? Now let's just think about these numbers. 32,000 is where the center of the hump is on our normal curve. 40,000, that's a number bigger than 32,000. So our z-score is to the right of the mean, which means it should be a positive value. And we're going to see this here in a second. So this is basically asking, if you buy a set of these tires, should you hope they'll last 40,000 miles or more? That is the mathematical equivalent of saying, what's the probability that y, or the mileage on my tire, is greater than 40,000? Now we've got to convert this 40,000 to a z-score. So we're going to say, what's the probability that my z-score is greater than this equation? So again, this is the number I'm interested in, 40,000, minus the mean, which we said was 32,000, all divided by standard deviation. And so if you do this calculation, you will get a z-score of 3.2. So we can rephrase this problem into one where we can use the z-table, and now we're looking at what's the probability that z is greater than 3.2. But now, again, greater than means if we were to draw this in with our normal curve, greater than means to the right of. So what's the probability that my area is to the right of 3.2? Well, again, the table never shows us areas to the right. So what we have to actually do is we find the z-score of 3.2. So it's 3.20, so we're in the first column. And that tells us that there's a 0.9993 or a 99.93% chance that z is less than 3.2. So there's a 99.93 chance that the mileage on my car tire will last up to 40,000 miles. So if I want to know what's the probability that my tires last longer than that, I'm looking at the area to the right. So I have to take 1, the area of the entire curve, minus this 0.993, and that's how they get this 0.0007. So they took 1 minus 0.9993, the number from the table, to get this 0.0007. If you convert that to a decimal, notice, or to a percentage, you're going to move this decimal 2 to the right, and so you still have this is a mistake here. This should be 0.07% chance that your tires are going to last longer than 40,000 miles. Very, very small probability that that's going to happen. Okay, the best way to get these down is just to really practice. So doing a lot of examples is really what's going to do it to solidify these concepts, because you got to be very careful. Like in this one, you know, the greater than symbol means to the right, and we know the table always works to the left, so you've got to subtract from 1. You've got to, you know, in the previous examples we subtracted different numbers, we're dividing different, I mean, there's lots to do here. So let's look at another one. So a tire manufacturer believes that the tread life of its snow tires can be described by a normal model. Same problem. Our mean is 32,000 miles, our standard deviation is 2,500. Approximately what percent of these snow tires will last less than 30,000 miles? So notice 30,000 is less than 32, so our z-score is going to be negative right away, because we know that this is to the left of this. And less than, that is the symbol we want to read our number right from the table. If it's less than, I can just take that table number and work with it. So again, in mathematical terms, it says what's the probability that my tire mileage y is less than 30,000 miles. And so we've got to take this 30,000, make a z-score out of it. So again, that's the number we're interested in, minus the mean of 32,000. Take that divided by the standard deviation 2,500, and that will normalize it, and we'll get a z-score. So we get, now what's the probability that z is less than minus 0.8? It's a minus z value, and it's less than, so we can just use the number from the table, and we look it up. A z of minus 0.80, first column again, is 0.2119. So there's a 21.19% chance that my tires will not last, will last up to 30,000 miles, but not more than that. Let's see here. Okay, I guess that was it for that one. So we figured out how long, what's the probability that my tires will last less than 30,000 miles, and it's 21%. Now in the second part of this problem, it's going to be kind of the same thing, but now we say what's the probability that my tires will last between two numbers. So we already know the probability that it'll last up to 30,000. Now it wants to know what's the probability that it lasts between 30,000 up to 35,000. So mathematically this says what's the probability that my tire mileage y is between these two numbers. And so we find z-scores for these two numbers. We already found this one, and now we've added this new one, 35,000. So again, it's the number I'm interested in minus the mean divided by the standard deviation. And so now we get what's the probability that z is greater than negative 0.8 but less than 1.2. And in this one now we have to find the two numbers associated with these z values. So we already found the minus 0.81, but now we have to find the z-score for 1.2. And notice again, if the z is less than this number, I can just pull the number right from the chart. I don't have to do any subtracting from 1 or anything like that. So if we go to the positive z chart and find the 1.20, we would get a probability of 0.8849. So we're going to use that number for our 1.2, and we already found minus 0.80 was 21.19, and so we're just going to subtract those two numbers. And so I've kind of drawn it here. This minus 0.8 translates to 0.2119 from the chart. This 1.2 translates to 0.8849 from the chart. And again, like I said, if you mess up this subtraction order, it's not going to matter. You're still going to get 0.6730, except you might have a minus sign out here. You always just take the number. So we're going to have 0.6730, or there's a 67.30% chance that our snow tires will last between 30,000 and 35,000 miles. Okay, that's going to do it for 7.2, and try these. Maybe sit down and maybe try to do these on your own without the video, and then see if you can reproduce these results, because these can be a little bit tricky. You got to really think about less thans and greater thans, and to the left of my z or to the right of my z, and you have to kind of really think it out. This isn't typically just kind of a plug and chug thing. We've got to draw pictures, draw those normal curves, and make sure that we're using sound logic and analysis when we do these problems. And we'll work some of these in class so we can get even more exposure to them.